So in that way, this thing is going on smoothly academic. 2 batches are graduated already now, BTech.
Sir, sir.
Only this one is we are unable to start new academic programs because we don't have hostels.
Hostels, yeah.
So
Without
we are
hostel, you
hoping
cannot start,
next
right?
year we want to start.
That too, so with COVID protocol, you need to have,
Correct.
more stringent requirement on hostels.
Correct. So that is where this August to November we called third year and final year BTech students
Sir.
for to the campus, and because we can accommodate about 700 students in the campus.
Okay, sir.
So now in the COVID protocol, it can be only 350 maximum.
Sir.
So that is where we invited only third year and final year BTech students. So
for them it is important because they have to complete the lab component, right, sir?
Definitely. And even for all these people, we are, especially final year students,
Sir.
We are telling them to complete all the labs before this November. Then next semester, we will send them back for online instruction.
Right, sir. Right. That's true.
Third year, they will complete maximum labs, but again, they will come back in 7th semester.
Sir.
Now 5th semester. Then January to April, we are planning to bring first year and second year.
Second year.
This is the plan as of now.
Very, very good plan, sir. Very.
What to do? We have no alternative.
But at least, sir, if final year they are able to complete their labs by this semester, November,
Correct.
They will go back because now they have one semester, they can do projects and all.
Definitely.
And you can call your first and second year. That is very good planning, sir.
No, that is correct. So that is the reason.
So which is the nearest airport, sir?
So Hubli Dharwad is a twin city. We have a Hubli airport, which has connecting flights to Bangalore, Mumbai, and Hyderabad.
Okay.
Of course, we also have a private airline connecting directly to Delhi Hindon Airport, not to main airport.
Sure.
So these are the 4. And of course, about 1 hour drive, we have another industrial town, Belagavi. And there also airport is there. There also we have connection to all these cities.
Okay. So
then international airport is about 3 hours, Goa airport.
Goa airport.
We are just 3 hours from Goa.
Sure.
So that is the way we are planning. Of course, mostly our international travels, we go to either Bangalore or Mumbai and take off.
So this time, sir, you are co-hosting this NCC, I think, sir.
Yes. We are co-hosting and just started preparation.
Yes, sir.
I think IIT Bombay will lead the effort. We will Dharwad, even Goa, Indore, and even Gandhinagar want to be part of the team. And
in JTG meeting, you mentioned that.
Correct. You are also there.
Yes, I was there.
See, we were thinking, of course, it will take a long time before we can host.
Sir.
Since Professor Gadre invited us, we thought we'll be part of the team.
Sir, great, sir. So, Dr. Udit.
Sir, we can start. So welcome, our speaker for this session. So first of all, I thank you for accepting our invitation to give a talk in this STC. So this session will be chaired by Dr. Preetham Kumar, who is Associate Professor in the Electrical Engineering Department, IIT Patna. So over to you, Preetham, sir.
Yeah, thank you, Dr. Udit. And it is really a great privilege for me to welcome Professor S.R. Madhavan Prasanna, sir. And he was associated with IIT Patna in the beginning when we started our campus in Patliputra in year 2008. So it is a very great privilege for me to welcome him again to IIT Patna platform. So good morning to all participants. Really, we are honored to have Professor Prasanna as one of the speakers here. And so Professor S.R. Madhavan Prasanna received the BE degree in Electronics Engineering from the Sri Siddhartha Institute of Technology, Bangalore, University, Bangalore, India in 1994. The MTech degree in Industrial Electronics from the National Institute of Technology, Surathkal, India in 1997. And the PhD degree in Computer Science Engineering from the Indian Institute of Technology, Madras, Chennai, India in 2004. And then sir is currently a professor with the Department of Electrical and Electronics Engineering, Indian Institute of Technology, Guwahati. He was earlier associated with Indian Institute of Technology, Guwahati. Now he is presently on deputation with the Department of Electrical Engineering, Dharwad, IIT Dharwad. And his research interests are in the speech and signal processing, and he's widely acclaimed researcher in the area of speech and signal processing. And today he's going to deliver a talk, very important talk, very interesting talk on potential of deep learning based speech processing. So we welcome Professor Prasanna on behalf of IIT Patna. Sir, over to you, sir.
Thank you, Dr. Preetham, for this invitation and also introduction. Thank you, Udit, for inviting me. Is my screen visible, Dr. Preetham?
Yes, sir. Yes, sir. It is visible, sir.
I'll go to full screen mode. Let me know whether it is.
Sir.
Is it okay now?
Yes, sir. Yeah. It is good, sir. Quite good, sir. No issue.
Thank you very much.
Sir.
Good morning to all the participants of this course. In the recent past, after this deep learning became very versatile, one of the frontier technologies to use deep learning and demonstrates its potential is speech technology. That's why the speech processing area has come to the forefront. Even though this area of research is there for last about 6 decades, now, especially last 1 decade, we have commercially viable technologies in the speech processing area. And this can be squarely attributed one of the points to deep learning. Of course, this deep learning is enabled by 2 factors. One is the computing infrastructure, GPU infrastructure that was made available. Also, easy way of collecting speech data using the network and computer networks, that is voice over IP as well as telecommunication network. Both these 2 factors indirectly helped the deep learning area to be used in the speech processing. And then now we see many commercially available technologies for the speech processing. One of the good example all of you might have seen is Amazon Alexa. In a few advertisements, you might have seen that. Or even Google Home, we have many other, Apple Siri, it started with Apple Siri, and many other commercial technologies have come. And people are quite happy in using them. After the successful demonstration of these applications for general interaction, now people started using these speech technologies in many sectors, like banking sectors for authentication purpose, or even automotive sectors, inside car communication, and many other areas as an example. So in this direction, in this talk, what I'll do is I'll only just give you a pointers that why deep learning became so successful in the speech processing area. Of course, many other experts will be talking about specifically different works that I have done using the deep learning model. Okay. Of course, these are some of the good books for speech processing and deep learning. Of course, when you come to the deep learning, the connections goes back to the earlier pattern recognition era, along with neural networks and other things. So in that way, the basic points are there in one of the very good books on artificial neural network written by Professor B. Agnanarayana. And apart from using deep learning for pattern modeling in the pattern recognition area or machine learning area, in the recent past, people have also started exploiting using this deep learning to extract features from the input signal. For example, this article has come in 2013 itself. Yoshua Bengio is one of the contributors for this deep learning area. They have written a paper on representation learning, a review and new perspective. And recently in the speech processing also it has come, deep learning representation in speech processing, challenges, research. So these are available in the public domain, whoever wants you can. And these are all some classical books in speech processing. Whoever is interested can refer to that. Of course, coming to the machine learning area, we have very classical books, Duda and Hart pattern classification, C.M. Bishop pattern and machine learning, some basic of artificial networks by Professor B. Agnana, Michael Nielsen neural networks and deep learning, Ian Goodfellow ETL deep learning, Charu Agarwal neural networks and deep learning, Mitesh Kapra's deep learning part 1 and 2 NPTEL course videos are publicly available. These are also wonderful resource material. And similarly, Professor Ali Godse's deep learning videos from University of Waterloo. So I have organized the presentation in the following way. I'll briefly introduce the field of speech processing. Then I'll talk about the deep learning area. After that, I'll switch back to the speech processing, which we were doing earlier before this, how we were doing before this deep learning came into picture. Then how using deep learning, things have changed. That's what I will. And also I'll talk about nowadays, we talk about using or applying direct raw waveform to the deep neural network and learning features from that, which is termed as representation learning. That also I will talk about and then summarize my talk. Before begin my points to put forward, this is one important technology in speech area, automatic speech recognition. This is taken from a public domain. This shows the progress in the word error rate. Word error rate is how many spoken words are correctly detected by the speech recognition system. Ideally, it has to detect all of them. So accordingly, the error rate will be zero. Word error rate will be zero. Of course, there are some additional pointers there. Just for discussion, let us consider only the number of words here. So if you see, starting from maybe 1992 or something, if you see the word error rate, it was there around 80%. It has gradually come down. Starting from 2012, where the first successful demonstration was done for building ASR system using deep learning model, the slope has become steep in reducing the word error rate. Now, if you see, currently in 2018-19, it says the word error rate has become less than 5%. 3 to 4% is the error rate. If that is the case, even humans also are expected to make this 3 to 4% errors. So accordingly, the deep learning models have shown their potential and hence resulted in the development of speech technologies which can be used for commercial exploit. That is the motivation where most of the MNCs are now developed their own speech technologies and using it for commercial exploitation. This one curve shows the significance of deep learning for speech processing. Okay, so that is the thing. Suppose if you consider this whole this deep learning area, generally the way I am projecting, we think that no, deep learning is such a great thing and this technology, and we need we need not worry about other things, and this is going to stand, and the speech processing area, then there is no research issue to address, and that is not the case. Deep learning is only a latest technological trend. Of course, it has shown significant improvement in many areas, including speech processing. However, if you look back into the history, in the field of computing, people initially thought we use computing devices, or basically computers, as a glorified calculator which reduces the human labor for computing purpose. Essentially, you want to do accounting and all those things which people used to do paper and calculator mode. Now we want them to, of course, that was the motivation. But quickly, when the field of computing came, the computing fraternity felt that this is not a great challenge. Okay, so even if you want to count billion numbers or process billion numbers, we can do it in a fraction of a second. But what is the real challenge for a computing field? That is where people started thinking about taking humans as one reference and computing field as another reference. These are two parallel verticals. Can we mimic some of the human abilities? As humans, we have abilities to interact with external world. Can we mimic some of the abilities of humans in the computing platform so that now we have computer to computer communication is straightforward, human to human communication is straightforward, whereas when we come to human computer interaction, there are a lot of difficulties. This is mainly because the architecture in case of computing is different, whereas the architecture for human operation is different. So as a result of this, because of this fundamental architectural mismatch between the humans and computers, it is not straightforward to bring human-computer interaction. Of course, initially when the 1960s, when they started, oh, we will be able to solve this problem in a decade or so, quickly they realized that how brittle their solutions or efforts are. But what is interesting is this type of trying to bring a bridge between human and computers for human-computer interaction resulted in many research fields and also provided a lot of opportunities for the advancement of the field. And many research areas or research fields started in the field of computing to enable this. If you see computers, that is essentially computing, we always talk about faster processor. From one generation to the next generation, we always look for a better processor. And also we need more memory in our computing systems. Of course, we want more in terms of faster processor, more memory, but we want the cost to be reduced. And of course, we use computers for automation purpose, and it has resulted in networking of computers across the globe. We have this internet where we can access all the information at a click of our mouse in our terminal. Now we have cloud infrastructure through which we can do any sorts of a very complex computation without having a physical infrastructure in our location. And also the latest buzzword of artificial intelligence also can be attributed to the field of computing. This is all the story with reference to the computing, if you see the journey of computing. Alternatively, when I come to humans, there are hallmark qualities of humans. All of us have been endowed with what is called cognitive ability. With the help of our cognitive process, we have very unique way of interacting with external world. We have sensory mechanism, very sophisticated sensory mechanism. With the help of cognitive ability and sensory mechanism, we can learn representations as we sense the data through external environment or sense the signal through external environment. In case of speech, if I see, I can hear the speech signal through my from the external environment through my ears. The ears is the sensor through which we are funneling in the speech signals or audio signals. And our ear converts that acoustic signal into some sorts of representation on the auditory nerve fiber and sent it to the central nervous system or brain. And the brain will do what we call a pattern way of processing. Pattern way of processing means why I'm highlighting this point is both representation learning and pattern way of processing. This is a very unique way of learning relevant information from the incoming signal. Also, modeling information from those representations, that is the pattern way of processing, which is not the case when I do data processing on a computer. That is where the human way of communication is quite distinct compared to the general computing that we do. And this can also be attributed what is called the natural intelligence that is endowed with all humans. So now if you see, when I go to the field of computing, there is nothing like a cognitive ability. There is nothing like a sensory mechanism with that. And always it talks about extracting features from the incoming signal. And it only processes data. There is no pattern way of processing. And it has no intelligence since there is no cognitive ability. That is where we talk about mimicking the natural intelligence associated with humans on a computing machine. That is why the field of artificial intelligence has come into picture. Now, if you can appreciate the two parallels in this society, one is the field of computing, the other one is the humans themselves as reference. There are fundamental differences in the way these two work. So accordingly, how do I bring them together? Of course, with this, I'm not saying that we are belittling the importance of field of computing. The advancement of computing has really helped this generation to reap the benefits of this field of computing. All of us, without any exception, we can appreciate how the world would have dealt the pandemic without this. Of course, people say centuries, every century, one pandemic wave comes like this. I don't know in 1920s how they did it. But now with the latest technological trends, we got used to this. Without computing, it would have been next to impossible for many activities to continue unabated, including our academia. Thanks to all these VC platforms, all those things, we are able to come. That is the definitely a very good contribution from the field of computing. Now, suppose since I mentioned the difference between humans and computing, the experts in the computing or the researchers working in the field of computing, they wanted to mimic the human abilities. That is new challenges and opportunities for when we want to mimic these human abilities on a computer, it gives us new challenges and opportunities for computing. As a result of this, many areas came in the field of computing, like human-computer interaction, pattern recognition, machine learning, deep learning, artificial intelligence. Like these, many areas took birth and matured so that they stand as separate fields in the computing. When we say this latest buzzword of artificial intelligence, this is not the first time. Earlier also, we had in 1980s or so, the concept of artificial intelligence, which came into the field of computing. At that time also, it created a lot of hype, but quickly people realized that it does not have the potential. Whereas now, again, in 2010 onwards, this field of artificial intelligence again is making a big noise now. But this time it looks like it is not a brittle like what happened earlier. It looked like this now the computing field is fertile to realize some of the abilities of artificial intelligence. Essentially, it can be squarely attributed to the field of deep learning. When we say in this era, when we are talking about artificial intelligence, we are talking about exploiting the potential of the deep learning. When I come to the potential of deep learning, there are two important patterns, two important aspects. One is representation learning. The other one is the pattern way of processing. So these, if somebody is coming from signal processing, it is easy to appreciate this. Representation learning essentially focuses on feature extraction from the raw data. Pattern way of processing essentially represent training models, that is learning patterns and creating models with reference to that, then use that learned model for later decoding of pattern information present from the tested data. So the deep learning essentially deals with these two verticals. When this part when I go for, I'll quickly go forward. Human interaction with external world. We have 5 sensory mechanisms: auditory, visual, smell, taste, and touch. Sensing mechanism, we sample external world through senses, pass on the representation to brain via sensory pathways. Okay, we don't just blindly funnel the entire speech signal and take all the speech signal to the brain. From the ear, we extract only relevant representation and send it to the higher centers of learning. And our human brain, what it establishes is from the representations incoming, with repeated exposure to those representations, it creates some sort of patterns and stores them in the cognitive system and uses them as a reference when they want to deal with such instances coming in future. So that is what is that pattern way of processing. So it is all the hallmark of humans, all this representation and pattern way of processing, all are happening due to our cognitive processing. And also our cognitive processing, it is so sophisticated that there are centralized activities versus there are decentralized activities. Another important aspect is cognitive system provides us an ability to give selective attention. Selective attention, we are all witness to that on a daily basis. Suppose if I go to a party, where in a party hall we have hundreds of people assembled, there, as soon as you enter the hall, you feel like a commotion. Alternatively, you go inside the hall and you identify a small group of friends, then you make a small group there and start interacting with them. Even though the same level of commotion is there in the entire hall, you have no problem for interacting with your friends. And that is the hallmark of one of the hallmark abilities of the human cognitive system, that is selectivity. Till today, we don't know how to do that on a computing machine. So, and if you take all these human abilities, these are not, no, these are whole interaction with external world by humans is evolved in nature, optimized, and with an intention that maximum information exchange happens among human communication. Of course, this our computing field may have an history of about a century or two, whereas our human species has a extension of history of millions of years. And as we move on from one generation to other generation, the all the sophistication that are achieved are passed on through the genes to the next generation. That is how it. One simple example in our speech area is our human ears have been well optimized to listen to speech signals. Of course, relatively less for the beyond speech for the entire audio spectrum, but it cannot listen anything beyond audio range. And the way the human ear responses for as a function of frequency, if you see, it's very interesting to see that it gives me maximum amplification for the frequency range associated with the human speech range, typically 300 to 3000 hertz. That is the range in which maximum amount of energy is present in the speech signal. So there, our hearing mechanism is very sensitive, very low value also. So that is how every part in our human body is optimized over millions of years, and accordingly, maximum information exchange is. But what has happened is, when we started thinking about establishing this human computer interaction, since many of the things are not clearly known how humans do this, as scientists and engineers, we started mimicking them. Okay, now suppose human ears are there which can be sensitive to the speech signal. So can I have a mimicking ability for this? That is where the sensor concept came, which we have microphone, which converts speech from non-electrical, which is acoustic form, to the electrical form. Then, since the field of digital revolution took place, digital signal processing, all those things, on a digital computer, you want to process this, then we need to convert the, the speech signal, which is originally analog in nature, into discrete sequence. Of course, human perception system is completely analog, but since I want to mimic on a computing machine, we got the concept of sampling, and sampling theorem gave us an idea how to sample the signals. Then we had analog to digital conversion. Then we had this era of digital signal processing, like deep learning. People for 3 decades or so, 3 to 4 decades, were really appreciating the effort of signal processing, which essentially, coming to the field of speech processing, we use it for pre-processing and feature extraction. Pre-processing essentially refers to weeding out unwanted components and only pass on the required information to them. Suppose if it takes speech, pass on the only speech components, and any other audio component, you try to minimize their effect. And then feature extraction means, with the help of a suitable signal processing algorithm, you extract relevant dimensions so that you bring the information rate from higher dimension to the lower dimension. And this can be treated, a crude way of selective attention and representation learning, but they really don't mean anything compared to the sophistication that is there in our human abilities. Then came the field of pattern recognition, where we were talking about modeling and recognizing patterns. Here I would like to highlight that we need to understand the difference between pattern versus data processing, because the whole genesis of the field of pattern recognition is understanding the difference between pattern versus data. If as I told, when I go to the computing field, the von Neumann architecture suggests that we are going by, computers go by stored program and data concept. Anything you want to process, you load them in the form of data. And whatever you want to do on the data, you write a program which is an unambiguous sequence or set of instructions, And as when you execute the program, it will take the data point, then use that those data points, process it, and produces the results to the and gives out the result. For computers, if you see a simple example, if I capture an image using a digital camera, and if I go by a visual display, I can see what is the scene information that is present, or who is the person present in the image, like that when we take these images. Whereas for computer, since it does not have this cognitive ability to visualize or anything, for it, it is only just a two-dimensional matrix. And when you say I am doing image processing to do face recognition or something else, at the lowest level for computer, it does not matter. It cannot see any image or something. It is just a two-dimensional array processing you are trying to do. So that is what is meant by data processing. Whereas what we are talking about is pattern processing. For example, if I want to do face recognition, a face of a person is a pattern. So that is how each person's face is a unique pattern, and I need to model that pattern. So that is where this field of pattern recognition was developed and became a field in the computing, essentially to give capability for the computing to do pattern recognition. Then came the machine learning field during the turn of the century, where people felt when I do the signal processing and pattern recognition, we have made both these algorithms, feature extraction algorithm as well as pattern modeling and recognition algorithm, both have blind. That means to say, according to the set of equations, it will blindly process the data, and this signal processing algorithm gives the feature, and the pattern modeling, it will model the pattern and then do that. Of course, we may say, no, what is the big deal? The big deal here is when I'm doing a feature extraction by a specific algorithm, even though the speech signal has much more additional information, it will never look into that. It will blindly neglect and throw away that additional information. Same thing happens for pattern discovery also. I may be assuming from my hypothesis that, oh, this is the pattern, this is what is meant by pattern which I want to model from. Then, whereas that the data may be hypothesizing something else as a pattern. For example, speech or image, it's okay because we have a lot of domain knowledge, but there are many areas where I don't have the luxury of domain knowledge. At that point, if you use this conventional pattern recognition to discover the patterns, we may not be really hitting on the right spot to discover and model the pattern. That is where the concept of pattern machine learning came. In the field of machine learning, the flexibility was given for automated pattern discovery. Flexibility was given to automated pattern discovery. In the sense, we want to, the algorithm itself will have the ability to wade through the data and process it as a functional mapping. Essentially, when you're given data points, say X, and there is a connection for the output label Y, but you don't know how they are connected, there is a mathematical functional relationship. And the whole process is to learn the functional relationship. That is where, except for guiding the algorithm in the matter that whatever the pattern you have in the digital field of data, we can treat it as a functional mapping. So with reference to that, you can use this machine learning for automated pattern discovery process. That is where the concept of machine learning came into the computing field. Of course, people have a lot of, some people have a lot of uncomfortness in using the word learning, because learning is an hallmark ability of humans, that too cognitive ability. The cognitive ability is termed as learning associated with humans. Computer being a digital electronic circuitry, it does not have any of such capabilities. However, we are using this learning in this sense that I only state that the relation between the given data points and the outputs, what I'm expecting, there is a functional relationship. That functional relationship represents the pattern, and the algorithm has to discover that. Coming to the deep learning, Of course, initially they started with whatever this machine learning part of automated pattern discovery. People started using this deep learning for that purpose. Later, they extended it that even it can do feature extraction also. Whereas in the machine learning, we don't focus on feature extraction. We assume that the features are given. The data points which we are using as input to the machine learning algorithms, we assume that they are the features already extracted by them, that some process, I don't have to bother. So that to that extent, the domain knowledge is set to the background. So as a result of that, whereas in deep learning, given raw data, I can do all of these things, both feature extraction. And the distinguishing character for deep learning compared to the earlier trends is again mimicking one more ability of our human cognitive process. That is, when we learn and master over any particular concept, even at the first example exposure, I will not be able to learn all the nuts and bolts of that concept. First, I capture only some important distinctions. Then, after repeated exposure to such examples, I go on increasing the complexity of learning the concept. Over time, I will have a mastery over that concept. Okay, and that is called as hierarchy of concepts. When we say hierarchy of concepts, I don't have to discover, or I don't have to have complete exposure to all the concepts when I start learning. And this is synonymous with our human learning. So, Dr. Preetham, able to hear me clearly? Preetham or Udit?
Yes, sir. Yes, sir. You are quite audible, sir.
Okay, thank you. So, when I go to this hierarchy of concept, this is an experience in our daily life. We don't, when suppose I'll take an example. We did not start speaking from day one. We started producing only sounds, then started formulating few words, then phrases, sentences like that. And now it is an effortless mode of communication when you achieve the maturity. You can extend that. Even when you want to learn the written form of the language, we started with alphabets, then combining alphabets to form small words, then bigger words, and then phrases, sentences. Even for that extent, for example, if I want to learn driving, when you go to a driving school on the first day, you will not say, okay, you take the key and go to highway and drive it. That is the way to learn. That is not the way. They will allow you in a graded manner how to what basic concept first few days you should practice, and then use those practices to get comfortness over handling the things and over. So in that way, human way of learning is only by hierarchy of concepts, and we need not specify everything on the day one. And in deep learning also it is same. If I take a deep learning model, it has several layers of learning. When I take the raw data as input, the first layer in the learning need not extract all the information. That is what I want to say is, it need not extract the patterns present in the raw data. It can only extract some feature representations, whatever it is possible, some feature. For example, easy to say for an image case, it can extract some edges, visible edges. It is not that it first layer always extract all the edges. Maybe whatever is feasible, it will extract. Now, these learned information from the first layer passed on to the second layer. The second layer can use these learned representation and further improvise on developing better representation, and goes on finally after final layer. If you go, the entire image representation will be available in the final layer. So that is where the concept of this deep learning came into picture, and that is being exploited in most of the fields, including speech processing. Of course, this representation learning I have told. So currently, when we talk about representation learning using digital signal processing, we are talking about feature extraction. Whereas, and when I go for feature extraction by signal processing, it is essentially a linear processing. As a result of linear processing, whereas we know many of the processes in nature are nonlinear. For example, speech, if I take the generation process of speech signal is a nonlinear process. Similarly, the reception and processing, comprehension process of speech processing and nonlinear processing. Whereas on a digital signal processing, we just go by linear processing. If you want to have a better modeling of information and robustness to our technologies, we need to somehow get the nonlinear way of processing the information. That is where the deep learning comes handy to get the nonlinear representation learning from the raw data. And pattern way of processing, I told. Initially in 1970s, when the pattern recognition became a field in the computing, people developed a set of tools to mimic the pattern way of processing by the humans. But how much they were successful at that point of time was only to demonstrate that, yes, it is indeed feasible to mimic the pattern way of processing by the humans on a computing machine. Whereas the performance of that pattern recognition system at that point of time, 1970s and early 80s, was nowhere comparable to human performance. For whether we want it or not, when we are trying to bring this human-computer interaction, the reference point is how good humans are doing this particular task. When I go for speech recognition or speaker recognition, any of the speech-related tasks, whether your computer-based system will give performance equivalent to that of humans. At that time, it was not the case. Whereas in the current trend, where we are talking about end-to-end systems using deep learning, in many technologies, the performance is comparable to that of the humans. That is where the significance of deep learning comes into picture. Of course, we have these terminologies like artificial intelligence, pattern recognition, machine learning, and deep learning. We use them interchangeably. It's not an exaggeration if I use the word abuse, because we really, there is nothing like we are using some great artificial intelligence concept there, but we tend to recast whatever we are doing in the theme of artificial intelligence. Of course, we can use these terminologies interchangeably, but it really makes sense when we understand the nuances between them and differences between them. And then if you want, depending on the feasibility, you can look at it. When I go for artificial intelligence, this artificial intelligence field is entire field where you are trying to mimic the natural intelligence ability on a computing machine. Whatever you do, that comes under the vertical of artificial intelligence. Suppose if I want to mimic the pattern way of processing humans, pattern way of processing humans is a part of their natural intelligence. Thus, the pattern recognition also comes as a part of our artificial intelligence. When I go for machine learning, we also do pattern discovery by automatic pattern discovery we do, which is not unique. So in that way, the machine learning also comes under the broader field of artificial intelligence. Finally, you will learn representations and also discover patterns as a human cognitive system. So that's why this deep learning field focus mimics that ability. Hence, deep learning also comes as a part of artificial intelligence. As a bigger umbrella, if you see artificial intelligence, you have the pattern recognition, which is machine learning, and deep learning becomes a subset of the machine learning. Of course, these are the slides which I have explained, where what is meant by artificial intelligence and what is meant by pattern recognition, machine learning, deep learning. I will not go into deep detail of them. Already I have explained. If we want to get a pictorial visualization to find the difference between traditional machine learning and deep learning, because deep learning is treated as one sub-vertical in the machine learning field. If I want to see the distinction between them, in the traditional machine learning, all of us have done this job. Take raw input to your computer through any sensory mechanism, spend a lot of time as a feature engineer to analyze the nature of that signal. And based on that, you identify some cues, and maybe you have a domain knowledge on what cues to look for. Based on that, you write an algorithm to extract relevant features. Features are wanted information in a reduced dimension. Those features are available. Then use these features in traditional machine learning models like support vector machine, hidden Markov models, Gaussian mixture model, any of those things for a classification task, and then classification output comes. Whereas now if I go to deep learning, what is done is you apply the raw input as input to the deep learning model. And finally, I get the classification output directly at the output of the diploma. So in that way, you collapsed all this feature engineering, feature extraction, and traditional ML model into the whole model will do by itself. Okay. The plus and minuses of then are, so when I go for this feature engineering done by human expert, lot of domain, if domain knowledge is available, then that is the best thing to go about. So you yourself pinpoint and say, okay, this is what you have to look for, and I write an algorithm to extract that. But in that process, I can do only, if I want to extract by signal processing algorithm, I can do only if I have enough tools and techniques available for doing that. Otherwise, I'll compromise there and I will get a next level, lower level of algorithm to extract. So even though expert knowledge is available, but we will not be able to convert them into algorithm in a fullest manner. That is where the limitation of feature engineering comes into picture. Even the traditional ML algorithm also, it is dictated by the algorithm or the model that I'm using for pattern modeling. It cannot look anything beyond that. Whereas when I go for deep learning model, it is just several layers of nonlinear processing. And also we, except for connecting these several layers of this one, we don't dictate the model to learn or what to learn and what to discover. So as a result of that, this nonlinear processing, at least from the output we are getting, it shows that it is able to do a much better job compared to what we were doing earlier. Coming to the speech processing field, if we essentially focus on studying the nature of the speech signal and also the methods, specialized methods that have been developed in the field of speech processing to extract relevant information from the speech, extract and model relevant information from the speech signal. So suppose if I take message, I'm talking about information, I'm talking about message part. That is the very purpose of speech mode of communication. I want to exchange some message with fellow humans, and that is what is that message component. Even though that is the basic motive, several other components will be inserted into, naturally gets embedded into the speech signal, like the language in which the message is generated is included, speaker information is included, emotion information is included, health information, etc. Many more information components are included. Interestingly, humans have the ability to decode one or more of these components by their cognitive system. And each of them have their own application. Based on that, no human survives in the society. Now, when we are doing human-computer interaction via speech mode, each of these components will be resulting into a separate applications or task, like speech recognition system, language identification system, speaker recognition, and so on. Okay. Earlier, what we used to do is both feature extraction by signal processing and modeling by pattern recognition. Now we are doing both feature extraction and modeling by deep learning. Of course, if you see the speech processing area by comparing human versus computing machine, what we do in a computing machine, we are trying to mimic this activity. The speech signal in the external environment is available when we generate as acoustic pressure variations. And that first gets converted into mechanical vibrations in the microphones or our human ears. Then from there, it gets converted into electrical variations like bioechoed potentials in humans or electrical signal coming out of the microphone. And that is what is being exploited in human ears for comprehension. Same thing we are trying to mimic that on a. So the electrical is nothing but your bioechoed potential on the auditory nerve. And human ears are very good at processing the speech signal. This bioechoed potential, which is essentially the potential, bioechoed potential as a function of time, it is a two-dimensional signal that goes into our cognitive system. It makes a spatial representation in our cognitive system. Spatial, so how you can see some cognitive speech processing. If you see some papers, you will see some images, two-dimensional images like a X-ray image or something, which is essentially like patches of light intensities in different locations, but it is also along the depth across several neuronal layers. It is a spatial 3D representation it gets created. That is nothing but the pattern creation. And again, as a result of that, that knowledge will be used for discovering any information or information retrieval during testing or future instances. So thus, our human cognitive system is very good at modeling the information. Computing machine, we are just trying to mimic these activities for decades, starting from 1960s onwards. Our goal is only just to mimic, because we have not clearly understood, except that up to inner ear of the humans, and appreciating that as we speak, there is a bioacute potential getting generated on the auditory nerve fiber and traveling to the human brain. But once it goes to human brain, of course, if you do the scanning, you will see some patches coming. Beyond that, we don't know how exactly this pattern discovery happens, and also I use that pattern knowledge for doing things. So that is where what we have done is, okay, since we have not understood, we want to mimic in our own abilities. That is where the field of digital signal processing came and pattern recognition came. Then when we are trying to do pattern recognition through machine learning and deep learning, now in the recent past, the latest trend is using deep learning in most of the tasks. Of course, suppose if I take what we have done so far, if I see the whole speech communication chain, we have 5 distinct portions. One is cognitive system of the talker, that is A; speech production system of the talker, B; the external environment in which acoustic signal is flowing is C; then human ear is D; and human ear of the listener is D; and the cognitive system of the listener is E. What we have done is, we are witness to what is happening in A and E. However, we don't know how it happens. Most of the time, we are just trying to mimic these things and build our own systems. Now, with the deep learning, at least we are mimicking one more ability of the cognitive system. I'm not saying that we are doing anything great there, but at least we are trying to mimic this hierarchical way of processing by humans. That concept is taken, and we are trying to build a computational model for that. We should not say that no, we have completely decoded human brain activities. Just with that simple way of appreciating that hierarchical way of processing the concept, that has given good result in the field of deep learning. Of course, if you see the speech processing, starting from linguistic level, it goes to physiological level, it goes to acoustic level, then goes to physiological. You can take, it makes a complete round, starting from linguistic level, ending up in linguistic level. And from linguistic level gets converted to physiological level in the speech production system. Linguistic level is in the brain or cognitive system of the talker. A physiological level is the speech production of the talker. Acoustic level is once it comes out to the external environment. Again, in the ear of the listener, it goes to physiological level. From there, it goes to cognitive system, become linguistic level. That is how we try to derive the message part. Okay. One important thing in our human speech communication is self-learning also happens for us. When I produce speech, I'm not even though it is generating for others to listen, I also get a copy of that through my hearing mechanism. As a result of that, I can perfect my production and perception system. That is where the beauty of speech communication comes into picture. So, of course, now this technological trend has come. That's different, but we can't wait for this deep learning to come in 1970s and start building systems. At that point of time, we were having signal processing, and with the help of signal processing, we tried to mimic the production system. Just starting from these vocal folds till the nasal cavity, oral cavity, all this portion corresponds to a dual role of speech production as well as the other activity which is meant. And for that, they brought the mechanical model first. Then they brought a speech production model based on a signal processing technique called linear prediction analysis. What they have done is, the whole speech production system, this physiological system, can be treated as a time varying filter, digital signal processing filter, all pole filter specifically. And then an excitation has 2 excitation generators, like our function generators in our laboratories. And then once you put a model, your whole goal is to extract the parameters of these two models, excitation source model and filter model. Then you digitize and transmit only those parameters. You don't need to transmit the whole speech signal. And this, even though if you compare this model with reference to the actual speech production system, it is a much crude model compared to what is there, but it seems to be practically sufficient when I want to use it for a communication purpose. When people were talking about 1970s to build mobile communication systems, where at that time, if I take digital communication by PCM, where we were having 64 kilobits per second, what people are talking about, if I want to do mobile communication, I need data rate at much lower level, talking about less than 20 kilobits per second or something. That is where if I take our GSM code, our initial codec came at 13 kilobits per second. That level of significant reduction in the bit rate requirement was achieved by using this model, production model. Without this mobile phone would not have been there in our hands. If I take mobile phone, when I speak into the mobile phone, the speech signal is first decoded by taking this model as a reference, and only the parameters of this are digitized and sent to the receiving point. At the receiving point, you regenerate the speech using the same model. What I'm saying is, what I wanted to say is, it is not that no, using signal processing, then have we wasted our time? No, we have also done enough work in the field of signal processing using for the speech processing. This is one of the beautiful contributions in the speech processing field to get our mobile phones in our hands. Now, just by decoding, and people were curious about how human ear works. So by analyzing this in the field of what we call um, psychoacoustics, the acoustic pressure variations first convert into mechanical vibrations in our eardrum. That mechanical vibration through the middle ear goes to the inner ear. In the inner ear, we have a fluid-filled chamber, which will create oscillations in the fluids, and that oscillations are picked up, spatially separating frequency components, and then use that for decoding the information. Okay, that is how the frequency separation happens in the inner ear. So this is what is being studied, and people have, again, beyond that, the whole thing was done in the field of psychoacoustics, where human experts are used and asked to perceive different audio components that they can perceive based on some what we call controlled experiments. And many results have been put forward. And only two important results I show. One is called what is called the masking phenomenon. In this masking phenomenon, what human subjects felt was, suppose you have a frequency component of a very large amplitude or very large sound pressure level, and any additional components in the neighborhood, in a neighborhood range, cannot be perceived if the neighborhood component amplitudes or sound pressure levels are below certain threshold, and that is called as the masking threshold for this component. For example, we are showing pictorial. This is that the large volume sound or a large sound pressure level sound is called as masker, and any component in the neighborhood which is lying below the masking threshold is called the masked sound. So with the help of that, so anyway, even if from a digital signal processing point of view, this component is also there, this component is also there. But even if you code and transfer to the receiving point, you will not be, or code and store it, you will not be able to use it. That is where people exploited this masking phenomenon for doing data compression. That's where our MPEG audio codec is there, where the audio coding is done by significantly exploiting this masking phenomenon, reducing the data. Similarly, even for feature extraction for speech technologies, we have a well-known concept of MEL filter bank, where it's a non-uniform filter bank. The concept of non-uniform filter bank came to the field of multi-rate signal processing, motivated from the human ear way of processing. Human ear is more sensitive to the low frequency components compared to the high frequency component. And accordingly, you can have smaller bandwidth filters in the low frequency, whereas larger bandwidth filters in the high frequency. That was mimicked by using MEL filter bank. Of course, those filters are not triangular shape, in the human ear, but for our convenient of signal processing and equations, we have made triangular shape and seem to be fine, consistently shown good performance. But now people are trying to mimic this Bell filter bank, trying to derive this filter shape directly using deep learning representations and use that knowledge to process the speech signal. So that way, these three important results. One is the speech production model, then two important results from masking phenomenon as well as the Bell filter bank has revolutionized the field of speech coding, then audio coding, as well as feature extraction by signal processing method. So those were the contributions and milestone contributions from the signal processing area. But now in the deep learning era, we are trying to see any more non-linear. In the linear prediction model, we are assuming it as a linear model. Can we bring a non-linear model for speech prediction or speech generation? That is where we have indeed achieved that using deep learning model. We are able to generate speech nowadays, which are sounding like a natural speech from the text. Of course, you can code and generate a natural sounding speech by a linear predictive codec, but the input is speech there. Whereas now speech synthesis, input is text and generate the speech like humans, it is able to do it. Of course, when I come to the field of deep learning, there is always, Preetham, how much time I have, Preetham?
Sir, half an hour, sir.
When we'll have Q&A?
Sir, at 11:30 we will have Q&A, sir.
Okay, take it.
Maybe so, for 5 minutes we will have Q&A, sir.
Okay, no problem. Then I will try to conclude by 11:20 so that we can have some Q&A.
Sir.
Okay. So when I come to this deep learning, there is always a confusion between neural networks and deep learning models. Of course, the look and feel wise, the deep learning models also will show the same structure as that of the neural network. Many of the architectures are initial deep learning model architectures are derived from the notion of neural network architectures. However, there is fundamental distinction, at least in my perspective, in two directions. One is the number of layers in the deep learning model is significantly higher compared to traditional neural networks. So accordingly, in each layer, the number of processing elements and also the number of layers are much higher order compared to the conventional neural networks. If I take conventional neural networks, the objective there was just to mimic the parallel and distributed processing ability of human brain. Whereas when I'm looking for a deep learning model, the philosophy is to build this model to learn the information from the raw data as a hierarchy of concepts. That is one of the reasons why it is called as a deep learning model. I learn from hierarchy of concept, whereas low-level concepts are there, then use that low-level concept in a hierarchical manner to derive the next level of complex concept, finally terminate in the most complex concept which you are looking for. That is another reason for calling this as deep learning models. Of course, now we have many different ways of architectures in the deep learning model, which were not prevalent in the neural network era. For example, I need not have dense connection. I can have an opportunity for layer-wise dissection and observing what is happening there. Also, it is not that the raw data is fed only to the input layer. You can take that in somewhere in the forward layer also, you can use that knowledge. So many things have come. Many varieties have come in the deep learning model. So first thing is much higher number of layers. Second thing is hierarchy of concept, decoding hierarchy. Of course, then the next question comes, whether you call 5 layers as a deep learning model, 3 layers as a neural network model. There is nothing like a written rule or mathematical proof to say what is that when you call it as a neural network, when you call it as a deep learning. At least from the literature in the neural network, what was shown was there is one book by Connectionist Model by Professor Hervé Ballard and Nelson Morgan. They have shown in the speech recognition contest that you don't require more than one layer in the neural network era to model the information. One hidden layer with very large number of neurons is sufficient to model or extract features from the speech signal. It is not that it models every information. If you take 3 layers, 5 layers, 7 layers, at that point of time in the neural network, you are not gaining any additional information. Of course, that can be attributed to the limitation at that point of learning algorithms that were there at that point of time. But now in the deep learning era, you can, as you increase the number of layers, you can increase the complexity of learning. That is the distinction. Okay, that is what is the difference. So to say anywhere from 1 to 3 layers, people found some interesting results from neural network. Beyond 3 layers, it used to saturate. Okay. Whereas now in the deep learning model, we are talking about 100 layers, 200 layers, like that. Of course, there is no requirement that it has to be of 100 layers. You can train layer wise and see at the output layer, are you getting the required concept or pattern discovered? If not, you add few more layers for learning. Okay. So what is common? We are also trying to use that parallel and distributed processing concept, which was there in the neural network theory. Plus, on top of it, we are trying to see the hierarchy of concepts for learning. What is the breakthrough in deep learning is until 2006, community were not knowing how to train deep neural networks or deep networks. Even though many of these architectures or models were proposed as an advanced topic in neural networks. Convolution neural networks was there earlier. Time delay neural network was there. Recurrent neural network was there. Long short-term memory was there, which now people talk, now we are using them. But these architectures were proposed at that point of time itself. However, their performance was not that great. So mainly at that point, what happened was, when we are trying to learn, the only workhorse algorithm that were present in the neural network was the back propagation learning. When you're trying to use back propagation learning for many of these models, it was inefficient to do transfer the error from the output layer back to the inward layers. We used to end up in what is called vanishing or exploding gradient problem, where your error either vanishes after few moving inside for few layers or explodes, which has no benefit for adjusting the weights of those hidden layers. Whereas in 2006, Professor Hinton from University of Toronto, their group demonstrated that it is indeed possible to train each of these hidden layers as a separate layer. You take it out and train that layer separately. That is called as greedy layer-wise training. The concept of the word greedy comes into picture because we want to try and extract, that layer should act as a feature extractor, maximum benefit to extract the features. So whatever the hidden variable are, we call state variables in that, hidden information needs to be learned by that feature extraction layer. And then you stack them, all of them together. Then you get the big deep neural network, and then one fine tuning you do using back propagation learning for adjusting. That greedy layer wise training gave the breakthrough for the deep learning area. Of course, people, this I have already mentioned. Then people in 2007 from other deep learning network groups also, they indeed reproduced the same result and confirmed that it is indeed possible to do greedy layer wise training. I think from that day onwards, now there is no looking back. Now everybody generates or proposes new deep learning architecture. Of course, there are many learning strategies now, many different architectures, but the fundamental concept, all of them, is representation learning, pattern way of processing, hierarchy of concepts. These are the three principles around which. So this I've already mentioned. If I look into the machine learning field, the genesis is due to pattern recognition, to giving more flexibility to the pattern recognition. When you come to the deep learning, genesis is in neural networks, which has much more capabilities than this. But if you see, deep learning is a part of machine learning. Machine learning is indirect a part of artificial intelligence. Of course, when I go for speech processing in the past, we have done the speech processing using all of these in clustering, dynamic time warping, Gaussian mixture models, hidden Markov models, neural networks, support vector machine. Some of these are the most prevalent, especially Gaussian mixture models, hidden Markov models ruled the speech processing field for nearly three decades, 3 to 4 decades. Now we are all talking about deep feed-forward neural network, deep belief networks, autoencoder, generative adversarial networks, convolutional neural network, time delay networks, and so on. Its variants like RNN, LSTM transformers, all of them being used for the speech processing area for technology. For example, of course, we don't have to give more any significance to these numbers themselves, but relative trend we can see. This Professor Hinton groups, along with others from other research groups, parallelly tried out this. They used deep neural network for acoustic model, which is core kernel of speech recognition, from 4 speech groups, and the results are produced in Signal Processing magazine, which came in 2000. This is a landmark paper, which put a firm foundation for using deep learning to the speech processing area. There, suppose before that, what we had for acoustic modeling was Gaussian mixture model HMM, which was giving a phoneme error rate of 27.3. They developed using convolutional deep neural network with filter bank energies that gave about 20%, which is an absolute improvement of 7%, which was not achieved for nearly about a decade prior to that. So that is where every time it was only a delta increment it was coming, but this is suddenly a step change. Like, if you do some mistake in coding or something, you get some fluke result sometime. People felt like that. That is where parallelly 4 important research groups in US and Canada worked on this, and they independently reproduced the result, confirmed that yes, this is giving. So then, people started, exploring that. Of course, when I go for speech recognition, the goal is to recognize the spoken message. Here also, with that improvement, which came from 23% to 16%, absolute improvement in 8%. Similarly, 27 to 18.5, which is almost 9% improvement, which gave push our attention for the entire speech processing community to take deep neural network seriously. Of course, after that, there is no looking back. Even for speaker recognition and language recognition, people started using it. Earlier, we used to have Gaussian mixture model based speaker recognition. I-vector based speaker recognition was very important technology, which was there before this deep learning came. When the deep learning came, initially, they proposed using deep learning model equivalent of I-vectors. They proposed what are called X vectors, and then they used deep learning model themselves as to replace the and deep autoencoders to extract the bottleneck features, and finally these X vectors, which are directly from the deep neural network model. Here also, if you see from 7.5 in the I vector, just use the bottleneck features from deep autoencoder, it improves by 1.5%, and another 1.5% when I go for X vector. This is both this bottleneck feature and X vectors by deep learning models. Some 7.45 to 4.17, which is almost 50% improvement in the performance. So that is how in this field also they mastered. Same thing went story for spoken language recognition also. Coming to the speech synthesis, this is also another important field where we focus on generating speech from the input text on a computing machine.
Sorry for interruption. Can you go in previous slide?
This one? This one?
No, sir. Before that?
This one?
Sir, just before this.
This one?
No, sir. Please go ahead.
Ahead. Okay. Please tell me when I should stop.
Next. After that.
No, I think here you asked me to go back. This, 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 this.
Yes, this one. This one.
Please. Any clarification?
Sir, can you explain once again F bank?
Filter bank energies. Okay. Let me, I have to go back to this, this Bell filter bank. Suppose I take the set of frequency components, say this is from 0 to 100 hertz, this filter is, which is there, one filter. I multiply that with this triangular shaped filter and sum all of that value, that I call it as energy, filter bank energy. In that way, there is one energy because you are multiplying two amplitudes. One amplitude is from the filter shape, the other from the frequency component amplitude, and multiply and sum them, that I call it as energy. This is filter bank energy. Second filter bank energy from second filter, third filter bank energy from third filter. Like that, every filter combined response, I call it as filter bank energies. So if there are 40 filters, 40 filter bank energies will come. Once I have filter bank energies, I do inverse discrete cosine transform to get the Kepstall coefficient. If I don't do Kepstall coefficient, I just take filter bank energies, and those are called as filter bank energies used as features for acoustic modeling. Is it okay?
Okay, sir. Okay.
That is what meant by filter. See, initially when they demonstrated, they used, for example, initial versions, random weighted weight and deep belief network. They used Mel frequency Kepstall coefficients as the features. In place of that, they used filter bank energies, which is one layer before that, or one layer before that as features for the recognition. Okay. Coming back to the speech synthesis, this is one of the field where people struggled for decades to generate a natural sounding speech. Whatever study you do and whatever system you built, always the generated speech from the computer was a very synthetic quality, robotic quality speech. However, one of the successful thing was what we call concatenative synthesis, where essentially you store the waveforms and concatenate, join the waveforms. But that is not actual speech synthesis. Actual speech synthesis is you should take input text from text, nowhere from you have to generate the speech signal. And that natural sounding speech was realized by using deep learning models. There are a series of models came like WaveNet, Tacotron, deep voice, character to wave, so many things came, which we were talking about deep networks up to 30, 40 layers. For example, I'll go to the final value. There is a 5-point scaling for evaluating the speech coding subjectively by humans. We give them imperceptible or indistinguishable from natural speech. You give 5, and worst you give 1. Then like this, 2, 3, 4 are given intermediate range. For example, any GSM coded speech on our mobile phone on a 5-point scale, it is given 3.7, around 3.7. Whereas our PCM on a landline digital telephone has 4.5. Now, for a natural sounding speech, when we ask for English and Mandarin speech, human subjects gave on a 5-point scale 4.46. For Mandarin, they gave 4.25. For that, a deep learning based system using WaveNet gave a 4.21, 4.08. You can see it's almost comparable to human generated natural speech from a computing machine. That was the real one of the important achievements, milestone achievement from the deep learning model, apart from other technologies. Just to summarize in this slide, I have told, when I go for speech recognition, we have word error rate jumped down from 15% to 3%. Like speaker recognition jumped from 7.5 to 4. Speech synthesis, which was earlier was 3.86, jumped to 4.21. It is not just 0.5%, it's really a great improvement in the performance, which shows the potential of deep learning in different speech technologies. The other thing is we use a raw signal I mentioned. Earlier studies, they use a filter bank energies. Then later felt that you don't need to do that filter bank energies also. Directly, you can take spectrographic representation of the speech. This is two-dimensional signal when I record through the microphone. And that one, if I use a short-term Fourier transform and construct the spectrogram, where x-axis is time, y-axis is frequency, and the intensity represents the amplitude associated with that particular frequency. The time frequency variations are there. This is called as visible speech in the speech domain. We can use the spectrographic image as a speech raw data and give as input to the deep learning model. People found that this performance of this system is better than even using filter bank energies. That is where people focused on generating different ways of spectrograms by different ways. For example, here it's by short-term Fourier transform. People went by Mel filter bank and generated spectrogram. There are other filter banks also, like gamma tone filter bank, people generated filter spectrograms, different various sets of visible representation and exploited them for speech. And that now the other off late byproduct, as I showed in initial representation learning, instead of feature engineering, since I can do better by giving raw spectrogram as input to the deep learning, this field of representation learning came into picture, where feature engineering, of course, it is good, provided I have the domain knowledge and I'm able to extract all the information. Because if I take signal processing itself, it has its own limitation in extracting relevant information from the speech signal. Okay, that is where the representation learning came into picture, where from the raw data I will try to learn the representation. Of course, even though it is a catchy word now, basically that conceptually it is already done. We used to do when we do principal componented linear discriminant analysis. We take the raw data, from there I get the representation vectors like principal components, eigenvalues, all those. Similarly, nonlinear ones we earlier has kernel PCA, non-negative matrix. Even neural networks in the earlier era, what we're in, they are also nonlinear way of feature extractors, representation. For example, these two things, one we have in speech processing called tandem features, where you use a neural network model. The output of the neural network model are used as features for recognition further. That is a representation only. Even using earlier when we use conventional speech recognition, we used to use a small segment of 10 milliseconds, whereas I can use a longer stretch of speech signal. Whereas to avoid too many variations, I take a smaller stretch around a specific frequency component so that I don't really significantly violate that non-stationarity. This also processed through a neural network to get the feature representations. So this genesis is there, but now it became more prevalent in the deep neural network era, where instead of STFT spectrogram, I can use MEL filter bank based spectrogram or gamma tone based filter, only to emphasize the information that is available in the spectrogram. And people started using different deep learning models like RNN, LSTM, CNN to in a supervised manner, or generative adversarial network variation autoencoders for unsupervised manner to learn the representation that are present in the speech signal. Of course, now in the last few years, this deep representation learning itself has become a dominant area in the deep learning, which I mentioned for feature extraction. You can use it for anything. Dimensionality reduction you can use, data denoising you can use, to discover the cluster structures you can use, disentanglement, abstraction. Many of these tasks I can use deep representation learning. Well, there are different ways of representation learning. We are aware of supervised learning, unsupervised learning. We can also have semi-supervised learning, transfer learning, reinforcement learning. Even in transfer learning, either domain adaptation, multitask learning, self-taught learning. Many of these paradigms can be used for representation learning. Of course, these are all the few models where initial few layers I can use it as feature extractors, and then later layers I can use it for classification tasks. Here also, when I told layer-wise training I'm doing, I take that hidden layer, I train using a restricted Boltzmann machine. In that point, that layer acts as a feature extractor. Then I pull out this layer, make it as hidden layer. Similarly, restricted Boltzmann machine will essentially train the hidden Markov model layer, this deep neural network model layer 2, which takes output from this first restricted Boltzmann machine and takes as input. That is how the training has been done. If you want to do bottleneck feature extraction, I use this autoencoder. Same way, this variational autoencoder, where I try to learn the distribution rather than compressing the vectors. I can use generative adversarial network to learn the actual distribution of the data. This is one of the most powerful models people use in the deep learning. If you see the journey of deep learning, now the deep learning models are acting like deep learning based expert systems. We had the concept of expert system earlier, where knowledge based computing systems were developed by decoding the human experts' knowledge and coding them in the form of rules. Here, the deep learning models themselves decode the representations and discover the patterns. In that way, when I take end-to-end system, an analogy is to treat it as a deep learning based expert system. Now, compared to where we stand in the case of speech processing, if you consider the era of deep learning versus earlier, now it has become mostly data driven. You have more data, more complex model, more computing infrastructure you need, more complicated programs in the form of software, and higher computing power you required in terms of hardware. So this all resulted in better, significantly improved performance, as I mentioned something. And also earlier we were more domain knowledge, speech area. Now from domain it has become domain agnostic. You have data and you know how to program, and you have GPU infrastructure you can build. But the advantages of is when you go for software and hardware requirement, people, even though you need complex programs to run this program, run this system, build these systems, open source toolkits are available. Many open source toolkits for deep learning. GPU infrastructure is available. Even though it's costly, you can rent it out. If you don't want to afford to have your own, you can use it, pay and use model. Then we go for industry versus, a lot of industry partners are also working in the speech area. If you see industry versus academia, industry people are mostly data driven. Academia is more earlier traditionally from domain. Now they have also moved into data driven. However, we can complement each other, where if I take domain experts can really try to analyze what is the deep learning is learning in terms of representations and patterns and give interpretation for that. That is what is called explainable AI. Whereas industry people are very much interested in building systems which are human comparable to human performance. That is how this is a very fertile ground for anybody to work in the deep learning area. Coming to the representation learning, we are demonstrated that deep learning models can learn representations. However, what we need to do is we need to do a careful study in terms of its repeatable. We should treat this as a nonlinear signal processing area and look for repeatability and interpretability from the representations learned in the deep learning. Coming to the speech processing, if I take traditionally very important task for speech recognition and speech synthesis, at least performance-wise, they have shown that their performance is comparable to that of the humans. Now we can go for attaining to tasks which are much more complicated than this traditional speech recognition or speech synthesis. One thing is speech-to-speech translation, direct speech-to-speech translation. As humans, we are capable, if we are multilingual speaker, you can listen speech from one language, you can translate into other language and transmit. It's a very challenging, complicated task. Now we can be able to move to that level with the help of deep learning. Also, we can summarize the whole conversation in very few words, that is discourse thing, and we can find out the intent of the person by using intent. These are all higher cognitive tasks which we can try to do using speech processing area. Just to summarize, I gave brief introduction to deep learning, speech processing area, applications of deep learning and speech processing I demonstrated. I emphasized on the representation learning. I also briefed about the future of representation learning and future of speech processing. I think with that, I'll stop here. Thank you very much for your careful hearing. Maybe I will be very happy to take some questions if any of you have.
Thanks a lot, sir. It was really very interesting. And I must appreciate that you explained everything in very simple words. Even a beginner of BTech students or beginner, they can understand the concept of deep learning, machine learning, and how they're applied in speech analysis, synthesis, prediction, everything. It was really wonderful talk, sir.
Thank you.
I myself listened to 1.5 hour talk, and I'm really benefited by your such a very, very informative talk.
Thank you.
So now the platform is open for any questions from the audience. So there's a question from Shivam. And Shivam, can you explain the question, Shivam?
Sir, I can read out in the chart. You have told in
Yes,
ear anatomy part, why cochlea is more sensitive to low frequency. Yeah, so that's a very good question, Shivam. Essentially, see, when I take speech signal, the way the different sounds are structured, the vowel sounds will have most of the energy in the low frequency, and this vowel sound are the carriers of information, even though they themselves do not have much information. Like our communication carrier signal is there. It does not have information, but it is a carrier of information. And accordingly, this carrier will take the preceding and following sound information on it to travel, and most of them is available in the low frequency round. To make it maximum information transformation, it made more sensitive to the low frequency.
So there's another question from Rani Kumari.
She's asking to share the PDF and recording of the session. I will mail the PDF file to you, Preetham. And
sir.
Yeah.
Sir, one question from my side, sir. Like you mentioned that these deep learning models, this non-linear processes, right? Like compared to our signal processing algorithms, which are mostly linear. So by going from linear to non-linear, is it that we are increasing the complexity very much, or it is manageable, sir?
No, we are increasing the complexity very much, Preetham. Only thing is, the advantage here is, even though we are increasing complexity, at the first level, we are seeing the benefits of that in terms of modeling information which we were unable to do earlier, and using that knowledge for any practical task. But now the path laid in front of us is we need to understand how it is working, why it is working. That is not true. Still, there is a black box processing like thing.
And one more question, sir, for this, like you told, sir, mobile telephones, right? By use this speak codecs, we are around 13 kilobits per second. So do you think that in this user devices, mobile devices, can we use this deep learning? Because it is a complex one, but definitely it will have more applications if we use it in mobile devices.
Very good question, Preetham. Because now, of course, there is a vertical in area where we call edge devices. No, these are all edge devices. People are working on how to port these deep learning models onto edge devices. Because when I'm training a cloud infrastructure, I have a luxury of any amount of computing and memory. Whereas in the edge devices, what they do is they train the models, also try to optimize the models, and then bring it down to the edge devices. That is what they don't do training there. They train somewhere and optimize the models and download it to edge devices.
Edge devices.
Okay.
So, one more question, sir, from Alok Rai.
Using STFT images 2D CNN, if you use raw sound data to a 1D CNN for feature extraction, will be a good decision. Of course, now people have tried that also in the recent past. We can use that also. Something what is called wave to vec is there, where that is deep learning model. People have started using this raw speech signal waveform from the time domain as input. So there is any medical applications, especially to differently abled persons. So that's a good question, Malini. So see, I took speech processing as a case study, but before even speech processing, image processing well exploited this deep learning wave, even video processing. And in that way, any area is not exception for this. What I'm saying is it will not solve all the problems, but what I'm trying to say, this is the latest technology trend, which has given a step change in performance. Naturally, in medical applications also, definitely we can use. Only issue in medical applications, for example, bioinformatics or something, when you take each subject data as one example, the number of examples you may have will be limited compared to the luxury that we have in speech processing or image processing. In speech processing, before this deep learning came, we used to talk about using 5 hours of speech data for training a speech recognition system. Now we are talking about training a speech recognition system using 50,000 hours of speech data. You can imagine 5,000 to 50,000 hours. You need the scale. But in medical domain, we have that problem where I can have medical X-ray images for about 100 subjects or 200 subjects, 1,000 subjects. I can't have million images. If you have that type of data, we can do. Of course, there are very alternative things people are trying out. Essentially, what they are trying to do is how to augment this data. Artificially, can I generate more data, which represent the variability that is there in the given data set. with the help of that, yes, we can use in medical domain also.
Sir, I have one question.
Please.
In terms of speech, which one is better? A feature application based is better, or machine learning based application is better?
So this question is again another important thing. See, if you have only few hours of data, then it is still better to go ahead with existing feature extraction method like meld frequency capsule coefficients and all those things, because already by domain knowledge and human experts, we are using those feature extraction methods. Because when we are telling about deep learning models, we are talking about thousands of hours of speech data for training the model. Okay. If you don't have that much data, it is suggested, of course, at least people say, you should have some 500 hours of data to get a respectable performance. Suppose you're working on developing a speech recognition for your language. But if you don't have, I think it's not just for the namesake, I want to use deep learning model. If you have limited data, then it is always good to still go ahead with conventional machine learning, support vector machine, or GMM and those things, extract features by signal processing method. But the flip side of that is when you write a research article for an international journal, reviewers will sit on you saying that already people have moved to deep learning. They are giving so much great performance. What is this? You try to compare your performance with the deep learning model. That is where the problem lies. But if you want to build a system, there is no problem. So you can try to. You have to see the research issue, which will not touch upon the areas where people have shown a step change in for speech recognition system. People are talking about word error rate less than 5%. Now you take one language and you have few hours of data using support vector machine, you show 10% of errors and you write a research article. Nobody will accept that, saying that no, internationally it is demonstrated that the error is less than 5%. Why anybody should accept such article? On the other hand, if you have some interesting research issue, which is different from this, except for the speech recognition performance, you want to bring out some uniqueness in that language. Suppose you're taken a tribal language in your area, which has a unique sound, which is not there elsewhere in other major languages of this. There you can still use machine learning and demonstrate the performance. Okay.
So we'll take
for beginners, which one is better, machine learning or feature extraction based?
So beginner, you should first get hold on to speech signal processing, feature extraction, and conventional models, because that is the background, and you should do some implementation there. But you should quickly graduate to the deep learning. Maybe
so
one.
we'll take the last question from Rituraj Biswas, sir.
Yeah.
So
he has told in a very question: speech processing being data driven versus through conventional signal processing concept, as rather a new research scholar in the field exploring employment incentives. Should I focus more on deep learning based? Would you say that? It's a very, very good question, Ritu Jai. See, if you want to make a career in industry, if you don't know deep learning, nobody will touch. Okay, because whatever the technologies they are building, they are on deep learning. They will not have time for you to give you 6 months to learn deep learning and then build systems. That is not academic space. If you want to make a career in industry, it's better to get on deep learning. Okay. Having said that, it is not that you have to wait for until you go to the industry or something. Even if you want to publish papers as a research scholar, you need to compare your results with the deep learning based systems. So naturally, you need to know there is no option left for research scholars. We have to get hold on to the deep learning. I am not saying that no, that is the only thing, but at least for comparison purpose, you should have that.
Sir, we are really thankful to you, sir. It was a wonderful session, and we have learned about deep learning and application of deep learning in speech processing, and you have given equal emphasis on this machine learning and signal processing aspects also. Yes. And I'm sure that the listeners have a good time. And sir will share this PDF with me, and I will get back to you. It will be transferred to you. right?
Yeah.
And
so
we
I
are
have
here.
sent
Thanks.
the PDF file to Udit. You can take
Sir,
from him.
sure.
Thank you.
So we should thankful to sir. Yeah, Udit.
Yes, sir. So thank you very much, sir, for giving your time for this precious knowledge. So I hope that the participants have learned a lot from this particular talk. So since he has talked about the basics of deep learning and machine learning. Again, sir, thank you all.
Thank you, Udit. Thank you, Pritam. See you.
Yes.
Sir, thank you, sir.
The
Thank you.
best. Thank you.
Thank you, sir. So participants, we will have next session at 12 p.m. Okay, so we will have a break for about 20 minutes. Thank you. Thank you, sir. Thank you, Pritam, sir, for chairing this session. Yeah.
Thank you, Udit.
Jha, sir, have you joined?
I'm joined and hello.
Hello, yes. You
I
can
think
start a 20-minute session.
okay.
Yeah, actually, participants can have a turn on the video. We missed that screenshot. Still, you can turn on the video. Not a problem. Yeah, participants, please turn on the video so I can take a screenshot. Thank you.
Udit ji.
Sir.
Okay, just testing that you are listening my voice or not.
Yes.